All right, hey, welcome back to Duran Learning. So this video is going to cover rectilinear motion. We're going to go ahead and revisit that topic from way back, in that first part of the course where we discovered that, hey, if we have a position function and we took the derivative of a position function, we received its velocity function, just like that. And then furthermore, we established that the derivative of a velocity function would yield its acceleration function. So I hope that we kind of sort of maybe hopefully remember this a little bit, because this is actually going to help us out in this topic. So basically we're just working backwards. That's all we're doing. If we have an acceleration function, and just to be clear, we're talking about indefinite integrals right now. So, and we'll get to definite in a second. But if we're taking the indefinite integral of an acceleration function, guess what we'll get? A velocity function. So basically we're just working backwards. So if we take the derivative, the integral is the antiderivative. So if we take the integral of acceleration with respect to time, we're going to go ahead and get that function's velocity, or that particle's velocity function, just like that. And then if we went ahead and just took it one step further and did the indefinite integral of a function's or of a particle's velocity function, hey, we're going to receive its position function, just like that. So that's the easy part of this video. So I hope this makes sense. Well, what we're going to discuss now is the topic of total distance versus displacement. That's what we're going to be covering. That's the most important part, because I hope that this first part wasn't too difficult to grasp, because all we're doing is working backwards. Now, when we introduce the definite integral, that's when things get very, very interesting, because there's a very good difference between computing a particle's displacement versus the total distance. So before we get to an example, here's what I mean. Let's say, my name's Anderson, and I'm going to go ahead and draw myself right there. Am I yellow? Nah, probably not. But here's the point. Let's go ahead and say I took 2 steps forward and 2 steps back. So there you go. That's all I did. I just took 2 steps forward, 2 steps back in a straight line. So straight line forward, straight line back. If I was asked, hey, Anderson, what was your displacement over that sequence of travel? I would go ahead and tell them, hey, well, my displacement is, well, here's where I started. I took 2 steps forward, 2 steps back. I ended up exactly where I started. So my displacement would be 0 steps, because I'm comparing where I was to where I ended up, which is, nothing. I didn't change. That's called displacement. Now, when we're talking about total distance, that becomes a little different. We now count all the steps. So not just the net forward and backward. We're going to count, okay, Anderson took 1, 2, 3, and 4 steps. Boom. That is my total distance traveled in steps, if that was a unit measure. So this is displacement. This is total distance. Just like that. So I hope that makes a little bit of sense so far. And yeah, steps isn't really a true unit of measure, so it's not going to help us out too much, but that's why I'm going to introduce this problem. So let's go ahead and erase all of this. And there we go. So let a particle's velocity be given by v of t equals 4 minus t squared, where t is greater than or equal to 0, and the velocity is measured in meters per second. So part A of this question says, compute the displacement of the particle after 4 seconds of travel. Part B is the similar, it's going to say, compute the total distance traveled by the particle after 4 seconds. So 2 things. Let's go ahead and start with that displacement. So the displacement, and here we have that velocity function, v of t equals 4 minus t squared. Sweet. Now, here's what we want to basically know. When we're trying to compute displacement or total distance, regardless, doesn't matter which one, we need to begin with the velocity function. If we had the acceleration, we'd be computing net and total velocity, which doesn't really make too much sense. And if we had the distance function, it really wouldn't make too much sense either if we integrated that. It's all because of the unit measures. If we integrate velocity, remember, we get position, or we get something that describes its position. And then when we apply it to the definite integral, that's where things get interesting. So if I were to just go ahead and compute the definite integral from 0 to 4 of my velocity function, that's going to give me the displacement. And guess what? The definite integral, remember, it computes the net area beneath a curve. And so it only makes sense that we should relate net area with displacement. Because remember, displacement only compares where you ended up and where you began. It just compares the two. And that's why if we compute the definite integral from 0 to 4 of this velocity function, it'll give us the displacement. So here it is. So if we went ahead and integrated, so we'll have the integral from 0 to 4 of 4 minus t squared dt. What this is going to give us is this will yield, that'll be the integral of 4, that'll just be 4t. The integral of t squared, that'll be t cubed over 3. And we're going to be evaluating this from 0 to 4. If we went ahead and evaluated this from 0 to 4, what that would give us is, okay, so 4 times 4, that's going to be 16, minus 4 cubed, that's going to be 16, then times 4 again, that's going to be 64 over 3. Boom, that's the 4 part. Then we're going to minus the 0 portion. If we subtract 0, what we're going to have is, let's go ahead and see. We're going to go ahead and have 4t, so that's going to be 0, minus 0, that's just going to be 0. Boom. So then our answer is just going to be 16 minus 64 over 3. And so what that would give us, well, we can just go ahead and convert 16 with 3 in there, and that'll be 48 over 3 minus 64 over 3. And we see that there's a difference of 16 in there. And so with that difference of 16, this is going to give us negative 16 over 3. And look at that. Our displacement is negative. That is odd, right? But actually, it really isn't. When we're talking about displacement, again, we're only comparing where we are now compared to where we started. So what this means, since we took an integral of velocity, this is going to be measured in meters. So what this means is that I ended up, or this particle ended up 16 over 3 meters behind where it started. So if we're discussing rectilinear motion, straight line motion. So if we're drawing like this 16 over 3, let's say this is where we started. After the 4 seconds of travel, ended up about over here, 16 over 3, which is about 5 1/3 away. So 5 1/3 to the left. That's why it's negative. If it was positive, it'd be 5 1/3 over here. But that's the beauty of it. That's displacement. It can be positive or negative. However, total distance cannot. So let me go ahead and just explain how to compute total distance. It's the same idea, really. There's only one subtle difference. One very subtle difference that is actually very hard to miss. So if we're trying to compute total distance, we're going to be computing the definite integral of the absolute value of our function. That's what we'll be doing. So here's why this makes sense. When we were to draw, let's say we were to draw this graph, right? Let me go ahead and use white. So if we were to draw the graph of this function, just like so, well, we'll notice this is 4 minus t squared. If we think about it as 4 minus x squared, if that helps you out, hey, go ahead. But basically, it's a parabola where our vertex is actually up here, and it's just a parabola, just like that. Just like that. That's exactly what it looks like. And its x-intercept over here, it's going to be t equals 2. This is exactly what the graph looks like. Now notice, when we look at this, hey, we have some shaded region right here, right? And let's say this is 4 over here. I'm going to go ahead and mark 4 right there. Now, if we look at this shaded region, hey, look at all of that shaded region below the x-axis. The reason our answer was negative for the displacement is because the area below the x-axis was greater than the area above. And so when we compute the definite integral, hey, that's the net area. So it only makes sense that our displacement was in the backward direction. However, when we want to compute total distance, we're trying to get all of these areas, we want to count them as positive. That's what we're trying to do. So instead of seeing this area below the x-axis, we shouldn't see that. Nope, not at all. What we want to do is, hey, when we take the absolute value, this is what happens. This bad boy is going to come up like this. And it's going to keep going forever and ever and ever. Go ahead, graph it. You'll see exactly what I mean. And so, boom, that's what we'll have. All the areas are positive, and then if we compute the definite integral from 0 all the way to 4, we're going to get a massively, massively positive number because we're computing total distance. So now the question becomes, how can we compute total distance? Again, how do we take the definite integral of an absolute value function? Well, here's the thing. If you've been watching this series, we would know by now that piecewise functions or well, absolute value functions are piecewise functions. That's what I'm trying to iterate right here. So what we can do is split this integral up. That's what we can do. So whenever you have a function that has a negative and positive region among its interval of your integral, what we want to do is split it up into the positive and negative regions. So we're going from 0 all the way to 4. And we've already noted that the x-intercept of 4 minus t squared, hey, if we want to find the zeros right now, we can go ahead and compute that, because then we'll just move the t squared over, take the square root of both sides, giving us plus or minus 2 as our x-intercept. Now we can ignore the negative portion because we're not talking about negative values for time, only positive. So, boom, 2 right there. If we plug in, let's say 1, we'll see 4 minus 1 squared, that's 3, that's positive, that's good. From 2 to 4, if we plug in 3, 4 minus 3 squared, or 4 minus 9, that's negative. And this is what we'll need to worry about. Since the 0 to 2 portion is already positive, we don't really need to worry about it, because the integral will already be positive. So when we take this definite integral from 0 to 4 of the absolute value, we'll need to split it up into the definite integral from 0 to 2 of our velocity function. And then what we're going to do is add it to the absolute value of the definite integral from 2 to 4 of our velocity function. Now here's why I just did that. We know for a fact that the area beneath the curve of this velocity function from 2 and beyond is going to be negative. And so what we can do to combat that, hey, just make it positive. Put the absolute value symbol around it. That's really it. That is exactly what I just did. And so we can go ahead and solve this now in the following way. So if we were to integrate or take the antiderivative of 4 minus t squared, we know that we would have gotten, just like last time, it was 4t minus t cubed over 3. So I'm going to go ahead and use that. That was the antiderivative. So what this means is for this 0 to 2 part, we're going to have 4t minus t cubed over 3 evaluated from 0 to 2, and then we're going to add it, just like here, add it to the evaluation of 4t minus t cubed over 3 evaluated from 2 to 4. Here's the only thing though. Remember, this portion, we're taking the absolute value of it. So first we'll want to evaluate the definite integral. We know it's going to be negative, and then we'll just make it positive. That's it, and we're good. So let's just go ahead and solve this bad boy out. So let's looking at this first portion. Let me go ahead and actually just scroll down a little bit. That way I have enough room to work with. Just like that. So what we have, that 4t minus t cubed over 3 evaluated at 2, what we'll have is 8 minus 8 over 3. And then subtract the evaluation at 0, which is just 0. And then we'll add it to the absolute value. Let me just use yellow just to really show that right there. And so again, if we evaluate this at 4, just like we saw last time, we would have gotten for that 4 evaluation, it would be 16 minus, that's going to be 64 over 3. Boom. Then we'll minus the evaluation at 2, which we know what it is. It's right there. It's going to be 8 minus 8 over 3. Sweet. Now what we have to do is just solve. So 8 minus 8 over 3, we can go ahead and use our calculators there. But I'm going to go ahead and solve by hand. So I'm going to make that 8. I'm going to turn that into a 24 over 3. Just like that. And so what this is going to give us is 16 over 3 right there. Minus 0. I'll ignore that. So we'll just add this onto. So 16 minus 64 over 3, just like we did last time. That's 64. We can turn that, or that's 16. We can turn that into 48 over 3. So 48 over 3 minus 64 over 3. As we saw, that's going to be negative 16 over 3. And then we're subtracting 8 minus 8 over 3. Just like we saw over here, hey, we converted that to 16 over 3. So we can go ahead and do that as well. Boom. So now that we're all set to finish this thing up, we have negative 16 over 3 minus 16 over 3. Hey, combining those, so that's going to be negative 16 over 3 minus 16 over 3. That's just going to be double, but in the negative fashion. So it'll be negative 32 over 3. But guess what? The absolute value portion, it's going to make this positive. We knew that this definite integral from 2 to 4 would be negative. We knew it. but putting the absolute value around it will make it positive. So now we have 32 over 3. Boom. And so therefore, we can go ahead and finish off this integral. So that's going to be 16 over 3 plus 32 over 3. That's going to be 48 over 3, which is actually divisible by 3. That's going to be 16. And boom, there it is. 16 meters is the total distance that this particle travels within its first 4 seconds. So let's go ahead and recap really quick because it's very important. Now, the displacement. If you have the velocity function, definite integral, no questions asked. If it's total distance, you are going to be taking the definite integral of the absolute value of your velocity function. And the way that you can break that down and actually integrate it is by knowing where your positive and negative regions are. We can first do that by going ahead and computing the zeros of your function, your velocity function. Remember, it has to be velocity. Compute the zeros of the velocity function. Find out where your negative and positive regions are. Then split that integral up, the integral of the absolute value, split it up into the sections that are positive and negative, wrapping an absolute value symbol around the entire integral for those negative regions. Because we know that they're going to be negative, so we just want to make them positive to count it toward the total area and not the net area. One more time, net area is displacement. Total area is total distance. And there we go. I really do hope this helps. Let us know. Go ahead and start practicing, and we'll see you next time.